Hello, and welcome to Linear Algebra. This is lecture 32, Singular Value Decomposition. Okay, so last time we talked about singular values, their definition, and existence of singular value decompositions for linear maps in the form of two orthonormal bases, one for the domain, one for the codomain, and a set of singular values. This time, we want to talk about singular values for matrices and about how you go about in practice finding the singular value decomposition of a matrix. Okay, so let's let B and W be finite dimensional inner product spaces. And T a linear map between B and W. So we saw last time that we can find orthonormal bases BV corresponding to V1 through the N of B, BW corresponding to W1 through WM of W, such that T of VI is equal to sigma I WI if 1 is less than or equal to I, less than or equal to the rank of T, which we will denote R, and 0 otherwise. Moreover, sigma 1 is greater than or equal to sigma 2, less than or equal, greater than or equal up to sigma R, which is strictly positive. These are the positive singular values of T. Okay, so we saw last time that it's always possible to do this, and that while the bases might change, if you were to do it a different way, the singular values will not change. Right, now if you were to look at the matrix associated to T with respect to these bases, let's call this sigma, capital sigma. This would be the matrix that has on its diagonals sigma 1 through sigma R and has zeros elsewhere. Right? It would be an m by n matrix with coefficients in F. So as I mentioned before, these are the positive singular values, and we will mostly be working always with the positive singular values, but you will find in other sources that the singular values are all of the elements of the diagonal here. So they are the positive singular values and then a bunch of zeros, however many zeros you have on what's left of the diagonal, right? So until you reach one of M or N. Okay, now given a matrix, well, of course, because matrices and linear maps are so closely related, the singular value decomposition for T, for linear maps, gives us a singular value decomposition for matrices. So, you could, for example, think of A as being the matrix associated to T with respect to the standard bases for some linear map T between Fn and Fm. So now that we have a linear map, we can do what we did last time to find orthonormal bases. Our bases associated to T as above. And what you can do is right. So, okay, it's unfortunate notation, but it's standard to denote the matrix containing all of the vectors v1 through vn by capital V, and the matrix containing w1 through wm as columns by capital U. So hopefully it won't be too confusing that this is the matrix V. So maybe what I'll do, sorry for moving backwards, I'm going to put V tilde and W tilde for the vector spaces, just to avoid confusion with the matrix. Okay, so here the bases are V tilde, W tilde. Okay, so now capital V will just refer to this matrix as opposed to the vector space. All right. Notice that in this case it's not actually overlapping notation, because in this case the vector spaces are Fn and Fm. But still, let's agree with that convention for today. So if these are the bases associated as above, and we write V as the matrix with columns v1 through vn, and U as the matrix with columns w1 through wm, so you'll recall this makes V the change of basis matrix from BV to E, and U the change of basis matrix from BW to E. Then A, which is the matrix associated to T with respect to the standard bases, I can write this as a change of basis matrix, and then the matrix for T, and then a change of basis matrix, right? And remember, this starts and ends with the standard basis, which means that in this composition, I have to start and end with the standard bases, right? But what I want to do is use here the matrix for T with respect to the bases for B and W, which means this one should end with the basis for V, and this one should start with the basis for W. All right, so this would be U sigma V inverse, right? But because V has columns given by an orthonormal basis, it's really easy to find the inverse of V. It's just V star. Okay, great. So this is just a translation of our theorem from last time to a theorem for matrices, but let's go ahead and write it down as a theorem. So if A is an m by n matrix with coefficients in F, and it has rank R, then there are unitary matrices. I remember unitary means that the inverse is the same as the adjoint, the conjugate transpose. There are unitary matrices U of size m by m, V of size n by n, and numbers sigma 1 greater than or equal to ... up to sigma r greater than 0, such that A is equal to U sigma V star, where sigma is a matrix of the same size as A. It satisfies that its ijth entry is equal to sigma I if I is equal to J and they're less than or equal to R, and 0 otherwise. Okay, and there's no need to prove it. This is what we proved last time. For linear maps, this is just translated to matrices. Just as before, we call sigma 1 through sigma R, like the positive singular values of A, call the columns of U the left singular vectors of A, and the columns of B the right singular vectors of A. And I didn't talk about this last time, but the reason this is left and this is right is because in the decomposition, the U goes on the left and the V goes on the right. Okay, so for example, if we have the matrix with columns 1, 0, 0, 0, 0, 0, 0, 2, 0, 3, 0, 0, 0, 0, 0, 0, and 2, 0, 0, 0, then, okay, W1 through W4 given by 0, minus 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, minus 1, and 0, 0, 1, 0 is an orthonormal basis of R4, V1 through V5 given by, okay, 0, 0, minus 1, 0, 0, 1 over square root of 5, 0, 0, 0, 2 over square root of 5, 0 minus 1, 0, 0, 0, minus 2 over square root of 5, 0, 0, 0, 1 over square root of 5, and 0, 0, 0, 1, 0. This is an orthonormal basis of R5 such that, right, so it's easy to check, A times V1 is equal to 3 times W1, A times V2 is equal to square root of 5 times W2, A times V3 is equal to 2 W3, A times V4 is equal to 0, and A times V5 is equal to 0. And hence, we can write A. Okay, so I'm going to have a 4 by 4 matrix here, where all I'm going to do is put the W's as the columns of this matrix. Right, so 0, minus 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, minus 1, 0, 0, 1, 0. Then I'm going to put the matrix sigma. So this is just going to have on the diagonal 3, square root of 5, 2. Notice that I listed these in decreasing order, as I should. And it's going to be a 4 by 5 matrix. 5. And everywhere else we have zeros. And then here I'm going to put the vectors V1 through V5. These are going to be the rows of this matrix, right? Rows because we're taking the conjugate transpose, and these have real numbers. So if they had complex numbers, I would put them as rows, but I would take complex conjugates. Okay, so I get 0, 0, minus 1, 0, 0, then 1 over square root of 5, 0, 0, 0, 2 over square root of 5, then 0 minus 1, 0, 0, 0, then minus 2 over square root of 5, 0, 0, 0, 1 over square root of 5, and then 0, 0, 0, 1, 0. Right, this is U sigma V star is a singular value decomposition of A. It is better to say a singular value decomposition as opposed to the singular value decomposition, because as we've talked about, these matrices are not unique. Sigma is unique, but U and V are not. As a simple example, if we were to change the sign of V1 and the sign of W1, that would not change the properties that we need. So they would still be orthonormal bases. It would still be the case that A of V1 is equal to 3 of W1. And so it would be a perfectly good singular value decomposition. So that is, I could change this. I could change this to a +1 and this to a +1, and it would be another singular value decomposition. Okay, so there's an example. This shows what it looks like, but this might not be very indicative of how in the world you would find this. So let's work out a little bit more theory that'll tell us how we find singular value decomposition if we're actually given a matrix. So here is a proposition. For any matrix A of size m by n, coefficients in F. So let's look at the set of all of the sigma j squared. So this is sigma j is a positive singular value of A. Right? This is the same as a set with the set of non-zero eigenvalues of A star A. And that's the same as a set of non-zero eigenvalues of A star. Okay, so finding singular values is not much harder than finding eigenvalues. You just have to first compute either A star A or A star. Sometimes one of them will be simpler to work with than the other one. Doesn't matter. You can use either one you want. Find the eigenvalues, and then the non-zero ones, take their positive square roots, and those give you the positive singular values of your matrix. Okay, so let's prove this. Well, let A equal to sigma, U sigma V star be a singular value decomposition of A. Okay, so now I want to compare these singular values with A star A and A star. So let's look at one of those. A star A, for example, well, A star A is going to be U sigma V star star times U sigma V star. And I can write U sigma V star. So remember, if you take the conjugate transpose of a product, you get the product of the conjugate transposes just in the opposite order. And if you take conjugate transpose twice, you get the original matrix. So here, we're going to get that. And then here, we're just going to have this. Now, U is a unitary matrix, right? Its columns form an orthonormal basis. So U star U is the identity matrix. So I can write this as V sigma star sigma V star. And now because V is a unitary matrix, I can write this as V sigma star sigma V inverse, right? So this shows that A star A and sigma star sigma are similar matrices, but sigma star sigma, this is a diagonal matrix with entries sigma 1 squared up to sigma r squared on the diagonal, followed by a bunch of zeros, possibly. So you would have n minus r zeros. And similar matrices have the same eigenvalues. Right. So what we've seen here is that if you start with any matrix A, then A star A is diagonalizable. And in fact, we've diagonalized it because we've found that it's similar to this diagonal matrix. Right. Similarly, right, to abuse that word, if you were to do A star A, now, if you were to do A star, this is similar to sigma sigma star, which is also a diagonal matrix. This would be a diagonal matrix. Just by direct computation, this is a diagonal matrix with diagonal entries sigma 1 through sigma r, sigma 1 squared through sigma r squared, and then a bunch of zeros. Possibly you'd have m minus r zeros there. So again, similar matrices have the same eigenvalues. So the eigenvalues of A star are the non-zero ones are sigma 1 squared through sigma r squared. Okay, and that's what we wanted to show. Okay, so let's come back to our example. Right? If you started with that matrix A, right? So if you start with this matrix, then the first thing you want to do is find the singular values. It's zeros. And the way you find the singular values is by looking at A star or A star A. In this case, for A is above, A star is equal to 5 0 0 0 0 9 0 0 0 0 0 0 and 0 0 0 4. So in this case, this matrix is diagonal. That's very special. It's just from this example that happened. But because this happens, this is diagonal. So the non-zero eigenvalues of A star are, let's put them in order, 4, 5, 9. Well, let's put them in decreasing order. So 9, 5, 4. Hence, the positive singular values of A are, well, the square roots, 3, square root of 5, and 2. Alternately, we could use A star, but A star in this case would be 1 0 0 0 2 0 4 0 0 0 0 0 9 0 0 0 0 0 0 0 and 2 0 0 0 4. And this is not diagonal. So it also has non-zero eigenvalues. Nine, 5, 4, but this takes more computation. to the term. Okay, so that's how you could have found the singular values. Okay, I'll come back to how you find the singular vectors in a moment, but let's think about another example just to show how this helps understand the action of the linear map multiplied by this matrix. So for example, if you have this matrix, then one singular value decomposition is this one. So this matrix would be U. Then we'd have a diagonal matrix, sigma, and then we'd have this matrix, V. So, for example, if you want to understand what is the action of multiplying by this linear map, well, it's enough to understand what is the action of multiplying by this linear map. So one way of approaching that is to look at what does this do to the unit circle. Right, so we have a map from R2 to R2. We could look at, no, sorry, this would be V star, which in this case is the same as V. We could look at what does this do to the unit circle. So V star is an isometry, right? Because its columns form an orthonormal basis. So it sends the unit circle to itself. Sigma multiplies the x-axis by 3 times square root of 2 and y-axis by 2 times the square root of 2, and then U rotates clockwise by pi over 4, which is 45 degrees. So in pictures, we're starting with a unit circle. So then we hit this with V star. And well, as a set, nothing happens. It stays a unit circle. But next, we hit this with sigma, and the unit circle becomes this ellipse. And then we hit that ellipse with U, and it gets rotated to something like that. And so altogether, that's what multiplying by A does to the unit circle, right? And if you were working more generally with any matrix A and its singular value decomposition, then it's still true that V star and U are going to be isometries, so they're going to be preserving length. So you can think of them as some sort of rotation, maybe reflection, but think of them as some sort of rotation. Then you can see that you're going to take the unit circle and end up with some sort of ellipse, rotated, and the singular values, well, the singular values are going to be the size of the axes of the ellipse, right? So the principal axis and then the next principal axis and so on. So you're going to end up with some, in higher dimensions, some sort of ellipsoid thing. And how much it stretches in different directions, that's given by the singular values of your matrix. Okay, here's a remark. Since we've just seen that AA star is similar to sigma sigma star, then any invariant of AA star is the same as the corresponding invariant of sigma sigma star. In particular, that's true of the trace. So the trace of AA star is equal to the trace of sigma sigma star And that one's easy to compute. It's just the sum, j goes from 1 to r, of sigma j squared. Thus, the Frobenius norm of A is equal to the sum, j goes from 1 to r, of sigma j squared, square root. But remember, the Frobenius norm is the square root of trace A star. It's also the norm that you get by thinking of your matrix as being one really long vector and then taking the usual or the standard norm of that long vector. In contrast, recall that the operator norm, we computed the operator norm in terms of the singular values. It's sigma 1, which is the same as the maximum of the positive singular values. Okay. Now we can express the singular value decomposition directly in terms of the singular vectors. And this is really useful when you want to use singular value decomposition to approximate a matrix with a matrix of smaller rank. So here's the theorem. For any A of size m by n, coefficients in F, there are orthonormal bases, v1 through vn of Fn, and say u1 through um of Fm, such that A is equal to the sum, j goes from 1 to r, of sigma j, uj, vj star, where sigma 1 down through sigma r are the positive singular values of A. Right, so this is just a restatement of the singular value decomposition that we had before. So there's nothing to prove. This is what you get if you just work out the product in terms of the rows of V star and columns of U. Let's see what this looks like in the example we've been carrying along. So with the same A as above, I can write A as 3 times the matrix product of the vector 0, minus 1, 0, 0 with the row vector 0, 0, minus 1, 0, 0, and then square root of 5 times the product of 1, 0, 0, 0 with the row vector 1 over square root of 5, 0, 0, 0, 2 over square root of 5, and then plus 2 times the matrix product of the vector 0, 0, 0, minus 1 with the row vector 0, minus 1, 0, 0, 0. Right, so, and you can read this off from the singular value decomposition that we wrote above. Okay, So as I said, this is really useful when you want to approximate with something of smaller rank. So let's state this as a theorem. Given a matrix of size m by n, with positive singular values sigma 1 through sigma r, and a matrix B of the same size, with rank of B equal to K, let's say strictly less than R, we have that the operator norm of A minus B is at least sigma K plus 1. With equality, if and only if B is equal to the sum, J goes from 1 to K, of sigma J, Uj, Vj star. Okay, so if you want to approximate in the operator norm your matrix A with a matrix of smaller rank, then the closest you're going to be able to get is sigma K plus 1, right? Any matrix of rank equal to K, this difference is going to be at least that big, right? And this is an achievable bound, right? So if you pick this matrix, then the distance will be exactly sigma K plus 1. And this matrix, notice, is exactly, take the sum that gives you A for the singular value decomposition, and instead of summing all the way to R, just sum until K. Right, so just truncate this sum when you've reached whatever rank you want, and that's the best approximating matrix of that rank to the matrix you started with. Okay, so let's prove this. We know that A is this full sum, right? Sum all the way to R. Also, by the rank nullity theorem, since the rank of B is less than R, we know that the span of V1 through Vk plus 1 intersects, let me give myself more space for this, intersects the kernel of B in more than just the 0 vector. All right, so why is that? Well, the rank nullity theorem tells us that K, which is the rank of B, plus nullity of B is equal to N. So if you do K plus 1 and add the nullity of B, this is greater than N, right? And then we've seen before that if you have two subspaces of some bigger space, so in this case Fn, and their dimensions add up to more than the dimension of the ambient space, then they have to have non-zero intersection. Okay, great. So they have non-zero intersection. Choose something in that intersection that's not zero. Let's let X be a vector in span of V1 through Vk plus 1, intersect the kernel of B, X not equal to 0 vector. And A times X is, by definition, sum J goes from 1 to R of sigma J, Uj, Vj star, X. Okay, now we recognize Vj star x as the inner product of x with Vj, right? So inner product of x with Vj, I'll put that on the left as a coefficient multiplying the vector Uj. And this, because x is inside the span of the first k plus 1 vectors, I can stop this sum at k plus 1 without losing anything. After the k plus 1, all of these are 0. So this is equal to the sum, j goes from 1 to k plus 1 of the same thing. Okay. So when we compute the operator norm of a minus b, this is, if I multiply this by the norm of x, this is greater than or equal to the norm of a minus b applied to x, right? X is not 0, so this left-hand side is not 0. So we're going to get something interesting, right? So let's see. So what happens over here? Well, let's square both sides so this is easier to compute. Then this is equal to the norm of ax squared. Why is that? Because x is in the kernel of b. So a minus b applied to x is just a applied to x. And if we take the norm squared, then, well, we've just computed what a of x is equal to this. So this will be, and the UJ's form an orthonormal basis. So this will be the sum j goes from 1 to k plus 1 of sigma j squared mod x Vj squared. And okay, so this is greater than or equal to replacing all of the sigma j's with sigma k plus 1 squared. Right, because the sigmas are non-increasing, so this one is less than or equal to all of the ones occurring here. But this, we notice, is just sigma k plus 1 squared times the norm of x squared, right? Because x is in the span of v1 through vk plus 1, and so this is equal to its norm squared. Okay, but now let's look at what we have. We have the operator norm of a minus b squared times the norm of x squared, bounded below by sigma k plus 1 squared times the norm of x squared. The norm of x is a strictly positive number, so if I divide by it, I can cancel it off from here. And conclude that the operator norm is bounded above by sigma k plus 1, and below by sigma k plus 1. Okay, great. That's what we wanted to show. And there, all we used was that the rank of B was equal to K, strictly less than R. Okay, so on the other hand, it's easy to see that if B is equal to sum j goes from 1 to k of sigma j uj vj star, then a minus b is, well, it would be the sum j goes from k plus 1 to r of sigma j uj vj star. right? So if you've truncated the sum and then you subtract it off, you get just the tail of the sum. And this has singular values sigma k plus 1 down to sigma r, strictly positive. Hence, the operator norm of difference is equal to sigma k plus 1. Okay. Okay, so that proves the theorem, except I overstated this. It should say with equality if you have this matrix. So this matrix gives you the approximates your matrix as well as possible, but it might not be unique. And you can see that by thinking, for example, of the identity matrix. If you want to approximate it with a rank 1 matrix, then of course there are many ways you could do that with the same distance. It's not going to be unique. It will be unique up to small changes like signs and stuff if all of the singular values are distinct. But in any case, let's just leave it with this. This is what we actually prove. We have equality if you pick this matrix. Okay. Surprisingly, I'll put this as a remark. This choice of B is also the best approximation of A from among all matrices of rank K when we measure the distance in the Frobenius norm instead of the operator norm. Right? So this really is the matrix you want to use if you want a matrix of rank K that approximates your given matrix. All right, and we'll stop there and pick it up from there next time.